Thank you for having me here. My name is Florence. I'm a PhD student in a group of Jonathan Home at ETH Zürich, and I'm going to talk to you about our progress towards generating a GKP Bell state by entangling two qunaught states with a beam splitter. So first of all, a bit of context. We are a trapped ion experimental group, and in our experiment, we can trap linear chains of ions. But in this talk, I'm going to focus about trapping a single ion. And if we trap a single ion in a harmonic potential, we can basically think of it as a mechanical oscillator. So in this talk, I'm going to talk about states of a quantum harmonic oscillator, how we can control them and prepare them in a single trapped ion system. And in particular, I'm going to focus on GKP states and grid states. And so for this, I'm going to give a brief introduction and remind you of this seminal paper by Daniel Kottesman, Alexei Kitaev, and John Preskill in 2001. So in this paper, they define a quantum code by defining displacements of the phase space of a quantum harmonic oscillator. So if I plot the usual phase space with position on the x-axis and momentum on the z-axis, we can define these Pauli operators by displacement of some length alpha along position here or momentum here. And you might remember from quantum optics classes that if we take the commutator of two displacements, this defines a geometrical phase in the phase space of the oscillator that effectively depends on the length of those displacements. So now if we choose this length to be exactly square root of pi, the geometrical phase that we will enclose will be pi, and we will get an anti-commutation relation of our two Pauli operators. This anti-commutation relation, it's usually what we want for a two-dimensional quantum code. So these Pauli operators, they have been defined also usually to, if you take the square of them, you want to find identity. So this means that if we translate this state by 2 root pi here, we should get the same state, effectively defining a two-dimensional grid in this phase space picture. So this gives us some stabilizer operator if we take this displacement of 2 root pi and gives this state some quantum error correction capabilities. So now I just want to flash some Wigner functions of how those states look like. So in here you have GKP state 0, and if we translate it along position by half a periodicity, we find GKP state 1. Good. Now, in their paper, Daniel Kottesman, Alexei Kitaev, and John Preskill also have considered other types of geometrical phase. In particular, what if you define a grid such that this phase is exactly 2 pi? It turns out the smallest grid you can define is taking alpha equals root 2 pi. And if you do that, you have such states such that those commutators, those operators x and z exactly commute. This is what we call qunaught states, because GKP states are a qubit, and some people talk about qubits as well in higher dimensions, but this qunaught state does not encode any logical information. It is a state living in a single dimensional algebra, and that's why we call this qunaught state. Now, how does all of this look like? Still in simulations. Here you have the GKP state, periodic by 2 root pi. And here you have the qunaught state, periodic by root 2 pi, with equal spacing between the peaks in position and momentum. So now here I want to emphasize that this GKP state is root 2 larger than this qunaught state. And this root 2 scaling is going to be essential for the rest of the talk, so please try to keep it in mind. So now, still in the theory, we are following this theoretical proposal by Walsh and colleagues in 2020, where they consider two qunaught states. So two harmonic oscillator states, they prepare them in a qunaught states, and they input them on a beam splitter. They find that if you take the beam splitter to be 50-50, you end up with a GKP Bell state. So this is a usual Bell state, 0, 0 plus 1, 1, but here the qubit is a GKP state. So let's try to convince ourselves quickly why it could work. And here I take a figure from their paper. On the x-axis, you have the position of one oscillator, and on the y-axis, the position of the other oscillator. This defines a grid of the correlations of the two positions that is spaced by root 2 pi. Now, if we input those two qunaught states on our 50-50 beam splitter, what this will do is that it will rescale the quadratures and effectively rotate this grid by 45 degrees. If we do that, we end up with a larger grid, larger by root 2. And effectively, it's a superposition of two grids. So the red grid here is spaced by 2 root pi, and it is GKP 0, 0. And the blue grid here is GKP 1, 1. So the superposition of those two grids gives us our GKP Bell state. Good. So that's the theory of the experiment that we want to perform in our system. So now, what is our experiment? We have an ion trap in which we can trap a single ion of calcium. Trapped in a harmonic potential, this single ion can oscillate around 3 orthogonal directions of space, and these directions are spectrally decoupled. So we choose 2 mechanical modes of motion of this oscillation, and these are going to be our 2 quantum harmonic oscillators. Now, an ion is also like an atom. It has a defined electronic structure, and we can pick 2 energy levels to define a spin that we can address via a laser. And the coupling between this spin and this motion is going to make us able to control the mechanical modes of motion via the spin. Now we can also control the modes of motions independently by controlling the electrode voltages that we apply. Good. Now, another bit of context. In our experiment, we are able to prepare GKP states of the motion of our single trapped ion. So this is not something new. It has been already demonstrated in trapped ions by our group previously and also in superconducting circuits. And for preparing those states, we apply an autonomous quantum error correction protocol. Again, this is not something new. It has also been used at ETH and at Yale in superconducting circuits. And you don't need to understand the details of this protocol. You can just know that it exists. We can basically correct for displacement errors along position and momentum, and transfer those errors from the motion of the ion to the spin, and then reset the spin. And we use this protocol in order to prepare GKP states. So the way we do that is that we prepare a squeeze state by modulating the trap potential at twice the motional frequency. Then we apply rounds of this protocol, and we end up with a GKP state. So I want to emphasize that this is experimental data. This is the characteristic function, so the Fourier transform of the Wigner function. And if we change the initial angle of our squeeze state, we can then prepare all of the states of the GKP block sphere. So now, back to our protocol, we want to prepare 2 qunaught states of the 2 mechanical modes of motion of a single ion. We do that by adapting this quantum error correction protocol, scaling the parameters, and applying it on 2 modes. So we apply it on the first mode, and on the second mode, all of this with a single spin. And doing that, we can prepare 2 qunaught states in the 2 mechanical modes of motion of a single trapped ion. So now on to the next step of our protocol, we want a beam splitter. But how can we make a beam splitter with a trapped ion? So this is the usual Hamiltonian of a beam splitter, like you have it in optics. And in trapped ions, we have those 2 modes, and then we can rotate them and modulating the voltage that we apply to our trap by the difference of the frequency of those 2 modes. And this gives us this interaction. To convince yourself that it works, you can look at the blue curve, where here we have a for-non swap of a fork-1 state between our two modes. Or in red, we have that if we prepare the two modes in a fork-1 states, then we can show some Hongo-Mendel type of effect. Okay, so now we have all of our ingredients. So we can place them all together. First, we prepare two qunaught states. Then we input them on our beam splitter. And here we choose the phase of those two ingredients such that we want to prepare this GKP Bell state of 0, 1, plus 1, 0. And then we do the readout. So the readout is done by mapping the correlations between our two oscillators onto our single spin. And then we can read out the spin. So we can then reconstruct the density matrix of our GKP Bell state. And experimentally, so far, we have a fidelity of 59%. So this is not so great. We are trying to understand why it doesn't match our simulated fidelity. And we are also working on local error correction of our Bell state. With that, I want to acknowledge my colleagues who also took part in this work. And if you're interested in more trapped ion and neutral atom work, please also go talk to Luca and Sylvan, who are at this conference. Thank you.
Thank you, Florence. Are there questions?
Thank you for the nice talk. For the characterization of the states at the output, what you do is measuring the characteristic function, or can you do homodyne detection, for example?
No, so in trapped ions we cannot do homodyne detection. So exactly, we measure the characteristic function. So the way we do it is that we apply this state-dependent pulse, and depending on so this is combination of sideband, so laser pulses that we apply to our ion, and depending on the strength of the laser drive, we can then map all of the different points of the characteristic function, so the Fourier transform of Wigner function, and then from that we can reconstruct the Wigner function and the density matrix of our state.
Okay, thank you.
Yeah, thank you.
Okay, I would like to ask a question. I always wondered if experimentally you're able to make perfectly orthogonal these GKP states, because in theory everything looks fine, but they always are probably more spread and not perfectly aligned in a grid. So does it affect your experiment?
Yes, so the question is about whether we manage to prepare orthogonal GKP states. And I would say not perfectly orthogonal, because they are not pure states, they are mixed states with our environment. We cannot say that those states are perfectly pure. So we can prepare, for example, GKP 0 and GKP 1, but I would not claim that they are fully orthogonal. Indeed, there is experimental noise that will creep up and mix our states with the environment. The biggest of that is fluctuation of the trapping potential that induces dephasing of the oscillator, basically.
Thank you.
So, yeah. Thanks.
I can also ask a question. In your simulations about the fidelity, this 10% increase that you get, what is your largest noise source that you assume in this simulation?
Yeah, thank you for this question. So in this simulation, we are taking, in principle, all of the noise sources that we know of in our experiment. So the biggest one is dephasing, fluctuation of our oscillator frequency, but we also have heating, decay of our spin, and things like that. We are in principle taking all experimental parameters, so we can characterize all of these noise sources separately and then feed the simulation with those parameters. But this is somewhat imperfect. Like we are not fully sure of exactly all of our noise parameters, and it turns out that in the experiment they are even bigger than the ones that we actually measure. So it could be that they were a bit underestimated, or it could be that there was some other experimental issue. This is still a work in progress, but we do hope that we can match this simulation that takes into account all of our noise sources.
Thank you very much. Then let's thank Florence again.